we talked about Huffman coding and that it always constructs a code, a prefix-free code for a given alphabet with given weights, so that it minimizes the sum, the expected code word length. But how good that is remains to be seen. And luckily, in the case of Huffman codes, and in this case of prefix-free codes, we have a fairly complete understanding of what happens. And this is where entropy comes in. That's why I asked before how many people have seen this. So maybe let me just show the answers here one more time. Also in the main video. So I asked you if you know what entropy in this information theoretic sense is and how it relates to Huffman coding. And quite a few people do know, but some others have never heard it. So I'll try to give somewhat a brief introduction without spending a heck of a lot of time. So what is entropy? Simply speaking, it's this definition that you see on the slide. It's defined for a set of probabilities. So we assume we have a random outcome here, numbers 1 up to n, but it could be other objects. The important thing is that we have a finite number of these, or a discrete number of outcomes, and the probabilities are given like this. So as always, the probabilities are between 0 and 1, and they sum to 1. That goes without saying whenever we say probabilities. And then the entropy is defined as this sum. We take the sum of all possible outcomes, the probability for that, and then log of 1 over the probability. Another way to write this is saying that it is an expected value over log of 1 over the probability for the outcome. That's just another way of writing this sum, because it's a sum that weighs things with the probability. That is an expectation by definition, but we will not really dwell on this interpretation much. That's just a definition. So maybe before we continue with this, we might want a small, tiny example. So say you have a fair die with a usual one, not the Dungeons and Dragons version with whatever many faces, with just 6 faces, the usual one. And fair means so all of the outcomes 1 to 6 happens with probability 1 over 6. So what is the entropy of this distribution, of this random variable of the faces of a die? Well, just look at the definition. So if I write it like this, I would have to copy 1 over 6 times, but I'm relying on your intuition, on your ability to guess that from the context. What it is the sum over, well, 6 times the same thing. So we can write it like that, but it's really a constant term inside the sum. And then we have 1 over 6, all right, just do it in slow-mo. It's 6 times the same thing and weight by 1 over 6. So that is a 1 times, and then log of 1 over, that's log of 6, right? And well, whatever that is, can we get log of, okay, this, maybe I should have prepared it. It's some number between 0 and 3, between 2 and 3. And well, whatever it is, maybe someone wants to compute it and send it in the chat or so, but it doesn't really matter much. So entropy has this feature that it sometimes has fractional values. Not always, though. Let's do another small example, a fair coin. So we have heads and tails, each with probability 1/2. If we do the same calculation, everything remains the same, except that this is a 1 over 1/2. So it's log of 2, and my log is always base 2, right? So that's just 1. So here the entropy is exactly 1. Okay, those are two simple examples. In the general case, if the probabilities are not all the same, then the sum doesn't simplify as easily, but you can still compute this for any given set of probabilities. What we need entropy for is as a measure of information content of a distribution. So how is that to be understood? In a sense, people often say it's the surprise, the amount of surprise that you get when you learn the outcome of such a random experiment. So say you throw a random die and you learn it came up with 5. How surprised are you to find 5? Well, entropy says you should be surprised 2 point something bits, whatever log of 2 is, log of 6 is. Okay, that's not very intuitive. More intuitive is using something like this 20 questions game. And I want to introduce this here in a very specific setting, namely the one that we will need for Huffman coding later on. So the game is as follows. You start with the unit intervals 0 to 1. Then I think about an interval, this little red one. It's somewhere in this unit interval. It's a subset of the unit interval, some interval somewhere. And then you start guessing. And your first question, before you start, you know nothing except that it's somewhere in the unit interval. And now you can guess, you can ask questions. Is your interval contained left of a certain point or right of a certain point? And a moment's reflection shows that the best you can do is to always ask, is it left or right of the middle point? Okay. And we'll make our life simple here by assuming that you never hit the interval. You would have to define this a little different. It works cleanest if the intervals have specific numbers only as their endpoints. So let's just see how this game goes in the cleanest version. Before you ask the first question, you know nothing. It could be anywhere. Then you ask, is it left or right of the point 1/2? And in this case, I answer, it's above 1/2. And so you have learned something, and you have spent one question. You have narrowed down the interval to this this range 1/2 up to 1. Then you continue doing this. You ask, is it above or below 3/4? And I say, oh, it's below. So you've learned a bit more, and you've spent 2 questions, and that's 2 bits of information. 2 yes/no questions. And you keep going. You ask one more question. I again say it's in the upper half. Okay, you learned that. And one more time, and then I say, well, yep, I'm spanning the range that you have. I extend over the entire thing. And so with 4 questions, you have learned what my interval is. In this clean way, that's what it works out like. And the observation to make here is that if you look at the length of this interval and you take log of 1 over the length, that's log of 1 over the probability for a random point on the unit interval to randomly fall inside my interval, then you get exactly 4. So if you want to think about this game, again, maybe a cleaner way is to think about not this interval as an interval, but you throw a random point somewhere. And you're asking, is it inside this red interval or no? And you know which intervals are possible up front. This we'll come back to this in the context of Huffman coding. Okay, so intuitively, what happens is we need to cut our interval in half that many times before we can reach the conclusion, potentially, if we're lucky in our how the numbers work out, we need at least that many halving steps before we can reach something that's small enough to be covered by this interval that you're looking for. And that's the way to think about entropy. It's a lower bound. It's what you definitely have to spend. It's not necessarily always attainable. So another way of saying the same thing is the entropy expresses the expected number of bits of yes/no questions you have to ask that are needed to nail down a random value when what you know about the random value is some discrete outcome, like it lies in the red interval. I hope this gives you some intuition for why this term makes sense. In simple terms, it is how often you have to cut things in half before you reach the size of this interval. What is the connection with Huffman codes? This entropy was just a definition that came out of nowhere. There's a theory behind this. It's called Shannon entropy because Claude Shannon introduced this, over 70 years ago. And it was very successful in many different fields. But the connection to Huffman codes is actually very intimate and also long known. The entropy formula essentially is a guidance to design good codes, because if you look at this again, this formula is essentially looking like our formula for the expected code word length for the quality of a prefix-free code, except that here we had this term stating the length of the code word we assign to an outcome, and now it's this term, and we say this is what we definitely need. So if we could encode the outcome I with log of 1 over p of I, p for I bits, we would be very happy. That's essentially the ideal code word length. Unfortunately, we cannot really do this in many cases. Say this log of 1 over pi works out to be 1.5. How should we assign 1.5 bits? This sounds, it's definitely not possible to assign a code word of length 1.5 bits. Not if you use binary encoding, but it is not as weird as it may sound at first. You can actually do something like this, where you achieve this on average, or you achieve this using different elementary units than bits. But we will not cover this here. And definitely in a Huffman code, the code words you assign have to be binary strings, and they can have 1 bit or 2 bits, but not 1.5. So this is not generally possible to achieve the entropy with Huffman codes, but we can at least show something very close to that. And the statement here is, if we have an optimal code, a Huffman code, and its expected code word length, then it is never better than the entropy. This is what I tried to convince you of from before. The entropy is, in a sense, a much more general lower bound. You cannot possibly get by with fewer bits, just because you have to learn the information. You have to cut down this interval often enough. But more importantly, Huffman codes are also never much worse. If you add 1 to the entropy, that's an upper bound for the quality of the code that you get from Huffman's algorithm. And what is the entropy in this case? Just to be clear, because we allow the weights in Huffman coding are arbitrary. They don't necessarily sum to 1, so you just have to renormalize those, divide by the total of all the weights, and then you get a probability distribution. So there's nothing magic in this formula for H. It's just normalizing the weights. Let's see how we can prove this. And the proof has 2 parts, because we have to prove 2 statements. We have this inequality and this inequality. And we will look at the first one first, because it's a little simpler. Because people have seen this. Maybe I don't spend too much time on this proof. Or some people have seen this. it relies on two other results that are simple results from mathematics, but I don't want to prove them in detail here. But I think the main message here is that entropy and Huffman codes might seem not so much related at first, but there is an intimate relationship, and that's what is in this definition. We start building a Huffman code with certain probabilities. So I will essentially call this P1 and up to P sigma. Just the normalized weights give us probabilities. We'd like to build a code, we build a code in Huffman's algorithm based on these probabilities. Once we have that code, or any code really, we can assign different probabilities based on the outcome, based on the code word lengths. And these are essentially given like this. So if you take negative powers of 2, so say if your code is like this, let's do a tiny example, A, B, C. Maybe A is just a 1, B is 0, 0, and C is 0, 1. Then you would assign A a probability of 1/2. Maybe let's add that into the table instead. Well, let's write it QC. So you would assign 1/2, 1/4, and 1/4 to these each. So you might not have had these probabilities when you started, but probably something in a sense close to it, approximate to it. Otherwise, Huffman wouldn't have built this code. But you could do this for any prefix-free code. It doesn't have to be a Huffman code. Now, there's first inequality, Krafts inequality. It basically just says that if you sum up these QI, it's at most 1. And in the way Huffman codes are built, it's actually equal to 1. And that one just says if you draw the code trie for this code, let's do that in our tiny example. So we have B, C, and A. What Krafts inequality says is, suppose each node splits probability in 1/2 to each side, then I can always project this onto the unit interval. And then every node splits this interval in half. And a leaf covers all the range that is at this point. So this one covers the entire, let's make this a little nicer, covers the entire range. So A has 1/2 weight in this code. Similarly, if you go one further down, then this node splits that here at a quarter, and then B and C each span this range, and so they get 1/4 each. Okay, that's a general mapping how we can assign. That's essentially what the QI does. And now Krafts inequality says that if I add these up, they're at most 1. And that's obvious because I started with the unit interval. And whenever I went down to an internal node, I just cut things in half. How could I ever have overlaps so that the sums get bigger than 1? That can never happen if I just split things here with 1/2, 1/2 each. Okay, so that's Krafts inequality. And if we have any set of numbers between 0 and 1 that sum to at most 1, we can use the second inequality, which is called Gibbs inequality. And that is basically this, which is true for any QI in 0, 1, so that they sum up to at most 1. That's another inequality that you can prove analytically using properties of the logarithm. So I don't want to do that here. My message here is, if you've shown Krafts inequality, you can use Gibbs inequality. So you can use this middle statement. which means you start with the entropy, but now you replace pi in the log by this other probability qi, or this other number. And you get only bigger by doing that. Intuitively, it says if you've built a code for pi with the best possible code word lengths, and you substitute the code built for some different probabilities, qi, you only get worse. That's what Gibbs inequality intuitively says. And that's, of course, also how we can interpret it for Huffman codes. Because this here is just the entropy, whereas this here is the code word length for our Huffman code, or for our code E, no matter what code it is. So the code word length for any prefix-free code is at least as long as h. That's the statement that we can prove here. And it's indeed true for any prefix-free code E, this lower bound. It doesn't have to be a Huffman code. The second part of the proof is this upper bound. So we now want to show that we can always have at most h plus 1 as the code word length in a Huffman code. This statement needs a Huffman code. And I'm aware that this looks a little scary, but the argument is not that tough. I just wanted to spell it out on the slides. But let's go through this a bit briefly. We start with the same trick. We define QIs that will correspond to code word lengths, but we don't have a code yet that is convenient for this. Instead, we do something slightly different. We take the ideal code word length, so our log 1 over pi, that was the ideal code word length from entropy. Now, we know we cannot usually achieve this because it might be a fractional number. So we round up. We cannot round down, that would be the entropy bound, but we can round up and try if we can achieve that. And the thing is, yes, the answer is yes, we can do this. So we take the ideal code word length, round it up, and then define a set of QIs as if we had this code already. So 2 to the minus of this rounded up code word length. So all the QI are powers of 2, negative powers of 2. Can be 1/2, 1/4, 1/8, 1/16, and so forth. Now, before we continue, let's observe that if I sum up this sum, pi here, but qi there, by definition, that is just this. If you just insert that and notice that the 1 over and the log just cancel the minus and the power 2 to the power, then this is the same as this. And now, because this term is always at most 1 bigger than the not rounded one, you can pull the 1 out of the sum, and then you're left with the entropy. Okay, so that's the first step. If we can achieve a code that has qi as the induced probabilities, we're good. Or if we have the rounded up ideal code word lengths, we're good. And now we will construct such a code word length. So again, this here is nothing but log of 1 over pi rounded up. It's just a fancy way of writing it, but it's convenient to use it that way. So we construct a code E prime so that all the code words are at most that long. And just by renaming the alphabet, we can assume that the alphabet is sorted so that the first character is the least frequent one. Now we construct this code very similar to how Huffman works, but with a very slight twist. If we just have 2 symbols in our alphabet, then there's not much we can do. We can assign the 0 bit to 1 and the 1 bit to with the other outcome. And we observe that then here, the 2 probabilities have to be at most 1 each, at most 1/2 each. Well, the QI don't have to sum to 1, so I shouldn't call them probabilities, but the weights QI or at most 1/2, because you start with something. The pi are less than 1, so that means this 1 over pi is bigger than 1, so log is at least 1. And if you round up, that's at least 2. And then, 2 to the minus 2 is already 1. 2 to the minus 1 is already 1/2. So there you go. So that part's fine. The code word with 1 bit is not too long. If we have more than 2 letters, then we do the same step as in Huffman. We take the 2 with the least frequency, merge them into a super character. But now, the key step that's different from Huffman's algorithm is this. We don't assign the sum of the weights. We assign twice the bigger weight. And then we recurse and compute based on the new weights the rest of the tree. Okay, so the rest of the construction is the same. But why is this allowed here? Why can we do this? If the 2 weights are actually the same, then this is just a fancy way of saying we sum up. But otherwise, if the 2 are different, that means that Q1 is the unique smallest value in this collection because things are sorted. And it also means because of these powers of 2, you can actually replace Q1 by Q2. Let's do an example. Say we have 1/16, then 1/8. Maybe I'll just draw it on the line instead. So here's 1/2, 1/4, 1/8, 1/16. So here's a 16th. Now, suppose we have a couple of 8s, like maybe 4 things. And another 1/4. Okay. And you notice I already left gaps here because the thing is, if this is our 1/16 and it's the only one, the next bigger is a 1/8. So we necessarily have a gap of 1/16 because all the other bigger numbers are multiples of 1/8 because they're negative powers of 2. So there's no way anyone can take up this slack of 1/16. But we know that these numbers sum to at most 1. That's from Krafts Inequality again. And because the p sum to at most 1. So because the q, it's maybe something to note here. The qi sum to at most 1. So there's no way how anyone could eat up this slack. So we might as well treat the 1/16 as another 1/8. And nothing else really changes. Now we only make a stronger requirement for this character. We want to have it higher in the tree. But it turns out this is fine. It just works out recursively. If you look at what you get from the inductive hypothesis for the super character, then it's the same statement with a new weight, and that's twice the big weight. That works out as this minus 1. And so because Q1 is at most Q2, that's good enough to bound the code word length for both of these characters. So we've constructed this way a code that has the ideal code word length rounded up. It's not the exact ideal code word length that the entropy has, but it's the closest you can imagine to get to it if you take every individual code word and just round it up. As this proof shows, this sometimes even leaves a little bit of slack. By rounding every code word up, you actually are stricter than necessary. It is potentially possible to round some of them down, but only some of them. It won't work if you round everything down. And you can't really rely on it. If in the worst case, you will have to round everything up. Well, maybe not. In the worst case, Not sure if you can if you can find an example where you can never round down. That seems counterintuitive. But the construction works if you round everything up, and it gives you the bound of h plus 1, and you can construct examples that come very close to this. Now the final step that's missing is, because Huffman constructs an optimal code for given weights, it is for the weights pi, it can't be worse than the code we just constructed. It's one other code for the same characters, so we might as well use it, but our Huffman code is never worse than this code. And the lengths of that code, we've just bounded that each of these code words is at most that long. So I just inserted that into the definition of L. And that again is at most h plus 1, as we've just shown at the beginning of this proof. So in total, we've proven this second statement as well. And in a constructive way, if you want, we can construct something that is like a Huffman code. It just is a slight twist in that we add this slack in the weight to make the construction cleaner. It's not obvious if you actually have to do this, and Huffman codes will never be worse, so you might not care. You can always construct your Huffman code with the same algorithm, and you can immediately get the guarantee that its expected code word length is at most h plus 1. Let's see if you're still with me, and I'll ask this little nitty question that asks to relate Huffman codes with some fixed length coding. I'm not saying what this fixed length encoding looks like. You're just supposed to compare this in the most general setting you can think of. So please have a go at this. When is Huffman coding more efficient than a fixed length encoding? And by more efficient, I think more precisely I would say more or at least as efficient as a fixed length coding. I'll give you a minute to digest this. And as always, we've had some 23 or so in the first question. So I'd love to see at least 20, better 25 people in the question. Well, YouTube claims I only have 20 viewers right now, so maybe 20 is already the limit for today. But we can do a few more. 13 is not quite 20. 14. Shall we leave it at, 17. Okay, 18. Thanks, guys. Good. Okay, maybe let's lock it in now then. And here's the results. So people have voted for very different things. I decided to mark these two correct in the strictest way of interpreting it. First of all, if you define more efficient, as I said, as never worse, then Huffman coding is, oops, I wanted to lock this really. Huffman coding is never worse than any other code, in particular a fixed length code. So it's always fine to use Huffman instead. You can never really pay more in the sense of code word length. The other statement here is also true. If you want to have a guarantee that you're strictly improving over a fixed length encoding, these statements here are not really enough. You need this, because remember what we've just shown, L of E is at most h plus 1, and it can be arbitrarily close to that. even though we don't know how h relates in general to log of sigma, the uniform distribution that would be optimal for the fixed length code, if this is less than log sigma minus 1, then that eats up the plus 1. So you would have log sigma, and that is the length of your fixed code. And here we have a strictly less sign. So in this, if you can show this, then your Huffman code is definitely better than a fixed length code. Okay, thanks for participating with this. That brings me to the end of the Huffman code section. I just want to recap how the actual encoding algorithm works. There's two phases, of course. There's two algorithms, of course, one for encoding and one for decoding. Encoding is slightly more complicated. There's two passes. The first one is we count all the characters in the text, in the source text, and count how often they occur. We need these frequency counts as weights for our Huffman code. In the previous construction, I always said, well, the weights are given, they're part of the input. But for encoding, you really rely on them to come from the text. So you start reading the text and you keep counting all the characters, and that's the weights you use for the Huffman codes. That construction is as you've seen in detail above. Now for encoding the source text, we actually have to store the Huffman code in one way or another. There's smarter and less smart ways to do it. I'll skip that part for this module. You can check the textbook from Sedgwick and Wayne. They discuss one option, a simple one. There's other options that are a little more space efficient potentially. So you have to store the code itself, and then in the second pass only, you use the code to encode all the characters in the source text. Okay. Now you will practice this in the tutorials in more detail. At least this second pass. We'll omit the encoding of the code, but the rest you will do. To decode, you first decode the code from, well, using a fixed encoding of the code. You have to decide on this, but again, we'll skip this. So we assume we already have the code read. And then you decode bit by bit from the coded text. Using the code trie, you just walk down the trie, and whenever you reach a leaf, you can output the next character, and that's it. As you notice, decoding is much simpler and also faster to execute. And that's not atypical in compression. You will see this happening again and again. So what have we seen about Huffman coding? The running time to construct the code is essentially sigma log sigma. That comes from the time to sort the characters by weights. Now, if the weights are smaller numbers, we can potentially sort faster than this. But if the text is very big, then the frequency counts will be way bigger than the alphabet size. So it's questionable what the complexity is then. You have to look at the parameters. But sigma log sigma is always possible with a comparison-based sorting method. Well, you can either sort up front or you build the priority queue, which is another way of sorting. So you get the sigma log sigma from the delete min steps and the inserts. Yeah, as an aside, there's a different algorithm that doesn't rely on a priority queue. If you have the characters already sorted by weight, you can do it in linear time. But we'll not discuss the details about this. The encoding itself is very fast. N is for the number of characters in the text, and C is the length of the code. So you have to, N is the number of characters in the source text. I should be explicit. So you read every character in the source text, obviously, but you also have to write the output. So this is the best you can hope for. There's no way to beat this apart from constant factors. Huffman codes in isolation might not be very widespread because, well, they tend to have some overhead coming from the fact that they have to fix an alphabet and have to fix weights, etc. But it is a vital component in all sorts of more advanced coding methods. So there's many variations that are in use, and you will find it as a building block in many more complicated encoding methods. We'll discuss that a bit later in this unit. So again, the good thing is it is a very clean, theoretically well understood method. It gives you the optimal prefix-free code, the optimal prefix-free character encoding. So it's the best possible you can do if you insist on encoding every character by itself. It's very fast for decoding. A slight downside is this two-pass approach for encoding. It means that you cannot use it in a streaming mode where you have just data flowing by and you have to process it as it comes. The two passes seem to work against this. There's hacks in practice to avoid this. You can restart after a certain block, or you can use adaptive variants. So there's a variant of Huffman coding that always maintains the best code for the prefix seen so far, but we'll not discuss these advanced topics. And another downside that's hard to overcome is you have to store the code alongside with the coded text, and that might lead to expansion. It might make the text bigger than what you started with if you're unlucky. But remember, we'll have to live with this fact there's no free lunch in compression, and in many cases, Huffman does achieve significant compression.